That was unfortunate. I had worked out a lot of the review and it had quit recording. So here's the finish up of the last one is you get the remainder of 9 long dividing. So on to number 5. Let me do this one again. That's fun. Okay. I should be even better at it the second time. So we're going to synthetically divide. Let's see. F of x is equal to 4x cubed minus x squared minus 12x plus 3. And it wants us to show that x equals the square root of 3 is a 0. And it wants us to then find all the zeros. Well, guess what? If we know square root of 3 is a 0, we also know square root is a 0. So I'm just missing one last 0. Remember, when you have a 0 that comes from a square root, that you know you're going to have the plus and minus. Doesn't matter if it's complex and you have 2i and then you know you have minus 2i because it came from a square root. If I'm given square root of 3, I know negative square root of 3 has to be. And so it wants me to show this through synthetically dividing. So I'm going to go ahead and I'm going to synthetically divide this with the square root of 3. We'll see what we get. Notice that all the terms are there in standard form, so I don't have to add a 0. And while this one might be a little bit harder, you could put like a little star like this, a little extra spicy because it's a square root of 3, but we should know how to multiply with a square root. Square root of 3 times 4 is just 4 square roots. And then I know if I add a rational number to an irrational, I can't combine those. They're not like radicals. So the best I can do is attach them through addition. Next thing that I want to do is I want to take the square root of 3 and now I want to multiply it, but it's by a binomial. You can either do this on the side like I'm doing, or you can do it in your head. I get negative square root of 3. Doesn't matter which order because this is not that kind of problem where I have to worry about the order. So I have square root of 3 when I distribute to 4 square roots of 3, which is 4 times square root of 3 times square root of 3 is 3. 4 times 3 is 12. And then when I add those, it's nice. And I get just negative square roots of 3. Now, when I multiply these together, I get 3. Square root of 3 times square root of 3 is 3. And a positive times a negative is a negative. Remainder of 0. Okay, so I broke down my cubic. These are the coefficients of my quadratic, right? Well, guess what? That's very, very ugly. I do not want to put that in the quadratic formula. I'm definitely not going to be able to factor that. So we're going to say, okay, if that was a 0, and we know negative square root of 3 is a 0, I can break this quadratic down to its linear, and then I'm done, whatever that result is. So I'm going to bring down my 4, and I get negative 4 square roots of 3. Oh, that's handy. And I get negative 1, and then I'm going to multiply these two together, and I get positive square root of 3, remainder of 0. There's my linear term. So I have 4x minus 1 equals 0. If I want to find that x-intercept, I get x is equal to a quarter. And then there is my 3 zeros, 3 x-intercepts. Good. Next problem is number 6. And number 6, we're going to look at multiple different ways. Okay, first thing that you're going to want to do is you could say, hey, I want to break this down to all of its zeros. What have we learned how to do? Synthetic divide. How did we pick numbers to synthetically divide? Well, we took our factors of our constant and our leading coefficient, and we have found all those factors and created a pool of numbers. And what stinks about 24 is it's like a way too many factors. I wish it was a little that involved. but it is. Right? So now all my lists, I'm going to list all those out again. Obviously going to be all the top numbers. And then I'm going to get a couple more from fractions. Like I get 1 divided by 2 is half. And then 2 divided by 2 is 1. 3 divided by 2 is 3 halves. And then 4 divided by 2 is 2. 6 divided by 2 is 3. 8 gets me 4. 12 gets me 6. And 24 gets me 12, which I already have all of those. So here's all a long list of numbers. And that it's not a fun combination. So I'm going to put my corner and 2, -3, and then I'm missing the quadratic. Got the linear, got the constant, so I needed a 0 placeholder. And then on number 6, you're just going to have to be a pretty good guesser. So what I would do is I would look at the key and I would guess correctly, but not really. I mean, you just pick numbers until you found one that got you a 0 remainder. And so I already know this is going to give me a 0 remainder. I'm not going to sit here and goof around. And so I get a 0 remainder. So I brought this 4th degree down to a 3rd degree, and I'm going to need to break it one more time to find the quadratic, which I can then handle from there. And so I'm going to do 3 halves because I know 3 halves is the answer. And so I'm going to multiply. Remember, you multiply by the numerator. 3 times -4 is -12, and then you divide by the denominator, which is 6, -6. And then I get 24 divided by 2, which is 12. Boom, 0 remainder, down to my quadratic. So I broke a 4th degree down twice. They're all factorable by 2. Pull out a 2. And then I'm going to look. Can I factor this thing? And the answer is no. So use the quadratic formula if it's not factorable. And so I'm going to do opposite b plus or minus the discriminant, all divided by 2 times my a. And then I'm going to do b squared off to the side minus 4 times a c, which I get 4 minus 16, which is -12. Now I know I have 2 complex solutions, so I don't have, these are not going to be x-intercepts. And then I have 2 plus or minus, well, let's see, square root of 4 is 2. So I have 2i square roots of 3. And then I'm going to divide these all by 2 and I get 1 plus or minus I square roots of 3. And then my other 2 real x-intercepts or solutions right here, these would be my x-intercepts, and these would be 2 complex solutions that would not show up. Okay, so that's one way. You're a great guesser. That wouldn't have taken you very long. But if you weren't, which you wouldn't have done because nobody would have picked 3 halves until the very end. So another way is, let's use our toolbox. This did not say I had to synthetically divide, and maybe it will on your test. But if not, we should always look in our toolbox to things that we already know. And grouping a 4-term polynomial is something we should know how to do. And I notice if I pull out a t2 cubed, I get 2t minus 3. And grouping works if I factor out the next binomial and I get a 2t minus 3. And when I factor out an 8, I get 2t minus 3. Boom, got my answer. Now I can take that common factor and factor it out. And then this leaves me with a linear, which I get 3 halves. Even if that's all you knew how to do and you didn't know how to break down the cubic, you could at least use that to synthetically divide and break it down once at least. And then my next is, this is a sum of cubes. So I could have gotten t, and then the cube of 8 is 2. Remember, you square, multiply the 2 together, 2t, and then square the last one, which is 4, same, opposite, always positive. And then here's my t equals -2. Boom, I got 2 of my reals. And how would I get my complex? Remember, I always said this one's my complex. Notice that this quadratic that I factor the 2 is the same here. So in the same way, I would have gotten 1 plus or minus I squared with the quadratic formula. But I already did that over there. I'm not going to do it again. Okay. Numero 7. Same thing, right? Number 7's a little bit easier, and here's why. Because my pool of numbers is not ridiculous like the other. When I do my P over Q, I get plus or minus 3, plus or minus 2 over plus or minus 3. So my factors, numerator are only 2, same thing, denominator. So my pool of numbers is reasonable. I get, when I divide the top by 1, I get 1 and 2. When I divide the top, I get a third and 2/3. So total, I only have 2, 4, 6, 8. And then I'll look at my sign changes. For my positive, I only have 1 sign change, so then I have the possibility I have 3 negatives, but it's been popular that we've had 2 complex solutions at the end. So if I'm going to synthetically divide on number 7, I'm going to use 1. So this is a fifth, a fourth, a third, a second, a linear, and a constant. Don't forget your zeros when you're missing. Lots of 5s. And I get my remainder 0. Yay, but now I'm only down to a 4th term. So maybe then I'll try, maybe -1 will work. Such a good guesser today. And then -3, 2, -2, 3, -3, 2, -2, remainder. So I went from a fifth. Now I divided by 1, and I got a 4th. Divided by -1, I'm down to a third. Now I got to pick one more. I'm just going to pick a random -2/3. Pick this one down. Again, when I multiply the numerator, the -2 by the 3, get -6. Divided by 3 is -2. Ooh, I love a 0. And then I get 0, and then I get a 3, and then I get a -2. Boom, 3x squared plus 3. I love it when my linear term is gone because that means I can solve by the square root method and not have to put into the quadratic formula. At -1 square root x equal to I. You might have said, well, I wouldn't have picked that -2/3. Well, eventually you would. You didn't have that many choices. So this one wasn't too bad. However, again, let's talk about our grouping. This is where I'd go first anytime there's four terms. Go back to what we've already done. So we only really want to synthetically divide when we have no options of factoring or solving any way that we knew how to do before. So it's kind of our last ditch effort because it requires so much guessing to get us there. Oops, I'm going to have to pull out a -1 of this one. So factoring by grouping works because I had the common 3x plus 2, x to the 4th minus 1, and now I get my x equal to -3/2. Boom, there's one of them. I say 3/2. I'm at -2/3. Now I have this little guy to worry about, but it's a perfect square. Right, and if that couldn't have factored out, you would have had nothing left to do. Like if you didn't know how to take that x to the 4th minus 1 any further, then you would have to synthetically divide this one. Remember, you cannot factor a sum of squares. So here's my 1 and my -1. That finishes out my reals. And then this x squared plus 1, right, I would just have to solve that quadratic. That's where I can match it. Remember, when you have a sum of squares, that's going to get you complex solutions. Difference of squares will get you real solutions that you can factor. So just remember, not everything can be broken up by that has 4 terms into grouping. We got lucky on both of those, but I always try to begin with. And if it's not, then I have nothing left to do. Okay, number 8. Here are the zeros of this polynomial. and I want to write it in factor form. First, the thing to look at is they gave me both complex conjugates. Sometimes they just like to give you one, and then you have to just assume the other one, because you know, just like the square root of 3, that the negative square root of 3 comes from it, because it comes from a square root. So I'm going to write these. Remember, if it's a binomial, you're going to need to hold that negative sign from your factor. Don't forget that this is when x equals 0. Sometimes we forget. We want to write like x equals 0. So now all I need to do is I want to write this polynomial all the way out in standard form. So we multiply our reals together and imaginaries together. So I can multiply my real right now. I have to hold off on that in a while because my complex isn't that easy. Remember, when we do complex, we're going to when it's a binomial, you're going to distribute your negative in. Okay. One choice is you could take all three of these terms and distribute them in the other one. There's a little trick. It's called regrouping. Group around your first two and isolate your complex, and what you create is a conjugate pair, because these are the same with opposite signs. So that means I can just multiply my a's together, or my firsts, and then my b's together, which is my i's, I squared. It's a conjugate, so it'll be a negative. And then I can just multiply these perfect squares together. I squared is -1, and then I have the negative from the subtraction. I have plus. And now I'm going to bring down my real. And now all I got to do is multiply these together. Remember, my goal is to get the standard form of the polynomial. Now I just have two quadratics multiplying, so I get x to the 4 minus 6x cubed plus x squared. This is where I always make mistakes. I'm going to try not to. So negative 3x cubed plus 18 squared minus 30x. Let's bring my x down. Minus 9x cubed plus 28x squared plus 30x. And there's my polynomial. All right. And number 9 and number 10, same thing. Says number 9, number 9, A and B. So one way to do number 9A is, hey, P over Q, so I know my possible rational roots are going to be all the factors of 10, which is reasonable. 2, 4, 6, 8 possibilities. Put in my corner. I got 1, 2, 5, and 10. All I got to do is break this thing down once, and I'm down to my quadratic. Notice Descartes, if I look at f of x, has no sign changes. They're all positive. So I know it's got to be a negative, right? So now I'm down to 4 choices. So what am I going to pick? -2. And I love that my linear term of my quadratic is gone, because then I know, boom, I've got a nice, easy square root method, and I'm left with 2 imaginary. So this only has one x-intercept at -2. That's my real. And I got 2 complex, or imaginary actually, and it's plus or minus I square root of 5. And those wouldn't show up as x-intercepts. Another way you could have done this one's groupable too. You could have grouped it and solved it and gotten those. So don't forget that method too. I'm not going to go over for time. Okay, and then f of x is equal to x to the 4th minus 9 squared minus 22x minus 24. This is a good example of not being groupable. Okay, there is nothing I can do here to group this problem. It just doesn't work. So I've got to synthetically divide. And then I go, oh great, another 24, right? But at least I'm not dividing by but 1. So all my or rational roots or all the factors. 24 such a okay, and here it is. So I'm going to look at my sign changes. I have one positive sign change, so then I know Descartes is going to say the other three are negative. And so since 3 is an odd number and it can only have one set of complex come out of it, I know I'm guaranteed at least one positive and one negative, but my negatives have the possibility of having 3 real. So if I was just randomly guessing on whatever number this is, on number 9, B, I would start picking my negative numbers and I would pick maybe -2. Okay, so I have a fourth, a third, a quadratic, a linear constant. 1, -2, -2, 4, -5, 10, 12, 24, remainder of 0. So there's my negative, and then I'm going to do 4 because I already know the answer. And 1 is 4 is 2 is 8 is 3 is 12, remainder is 0. So I went from a fourth to a third. Now I'm down to my quadratic. Oh, and you just want this to be factorable, but right, you can't. Because the only thing that multiplies to get 3 is 3 and 1, and they got to sum up to get the 2, and the only way you can get 2 is subtracting them, but my 3 is positive, not negative. So the good old quadratic formula, opposite b plus or minus my discriminant, 2 times my a, 2 times 1 is 2, and then work the discriminant off the side, and I get 4 minus 12, which is -8. So I do have 2 complex. Split up my 4, 8 is 4 and 2, so 2i roots of 2, all divided by 2, and I get -1 plus or minus I squared roots of 2. Boom, there are my 2 complex. Wouldn't show x-intercepts, and my real, well, those would be -2, and those would be my real x-intercepts. Okay, so what are we on, number 10? Oh, we get a reprieve from all the work. Number 10, list all the possible rational roots. That's a nice one. Not like we haven't just been doing that for all the other ones, right? So I have plus or minus 6 over my 2. That's my p over my q. And that gives me 1, 2, 3, 6, 1, 2. Let's list all these little suckers out. My possible rational roots. Possible, right? So I have all my tops. And I'm going to divide by my denominator. I get half. I'm going to divide by 2, right? So I've already divided everything by 1. Now I'm going to divide by 2. 1 divided by 2 is a half. 2 divided by 2 is 1. I got 1. 3 divided by 2 is 3 over half. And 6 divided by 2 is 3. Boom, there is my pool of numbers. It's a nice one. And number 11. Okay, so it says, assume 3i is a root of the polynomial p of x to x to the fourth minus 2x cubed plus 11x squared minus 18. Well, definitely not 4 terms. There's nothing I can do there. So I am going to synthetically divide with 3i. So a fourth, a third, quadratic, a linear. There. Bring down my 1. And remember, if I want to find all of the solutions, isn't that what they want to know? I want to find all zeros. So I know if I have 3i, I've got 3i. Right now I'm down to 2. So let's go find them. They could be complex too. I could come down to the quadratic, put it in the formula, and get no x-intercepts. So just like the square root of 3, I'm just going to use I. So I get 3i. And just like the square root of 3, I can't combine my real and my imaginary, so I'm just going to hold them through addition. Then I'm going to distribute my 3i, and I get 3i times negative 2 is negative 6i. And then 3 times 3 is 9, right? And then I have I squared, so that becomes, instead of a positive 9, it becomes a negative 9 because I squared is negative 1. And it just changes the sign. Now I'm going to add these two suckers up, and I get what? 9, 11, and 9 is 2 minus 6i. I'm going to distribute, and I get what? 6i. And I get negative 18i squared. When I distribute my 3i to negative 6i, I get negative 18i squared. That changes it to a positive 18. And just like that, the square root of 3, nice things happen at the end. And then I get negative 18 when I multiply this one, and I get a remainder of 0. So this is my third degree coefficients, right? So I'd have x cubed and then x, negative 2 plus 3ix squared. So definitely don't want to create a polynomial out of that. I want to use the other 0 that I know. And just like when I use the negative square root of 3, nice things should happen. So notice, nice things happen. And then I get negative or positive 6i. That's nice. And then I get negative 6i. Get my remainder of 0. Here's my quadratic. X squared minus 2x plus 2. You say, please be two real numbers, and it's not, because there's no factors of 2 that multiply together to get negative 2. So good old quadratic formula. So I'm going to do opposite b, surmise the square root of probably some imaginary part. I guess it could be a real number, just be irrational. Let's check it out. So b squared minus 4a c, 4 minus 8. Nope. Get negative 4. At least that's a little nicer. And I get x equal to plus or minus 2i divided by 2. I get 1. There's my 2 imaginary. 1 plus I. Remember, always coming in conjugate pairs. That's such a good example of that. Always coming in conjugate pairs. Number 12, back to a nice easy one. Use synthetic. Find P. We're going to say P of x is equal to x4 plus 3x cubed plus 10x 2. Find P of negative by synthetically substitution. So it's just asking you, what is the remainder, right? Say instead of plugging in negative 1 into the function, show that the result went by synthetic substitution. So I get negative 1, negative 4, 4, 4, negative 4, 6, negative 6, remainder negative 8. So you could always check your answer. Right? If I plug in negative 1 to the 4, that's 3, 1 cubed, 1. So I get 1 is 3 minus 10 is 2. And I should get negative 8. Let's see. Get 4 minus 12, which is negative 8. See? I could just double check if I wanted to make sure that the answer was correct. Number 13 is use synthetic substitution to find m if negative 3 is a 0. This is a fun one. It's like a Sudoku. So p of x is cubed plus, let's see, 1, 1, m, and 12, and what do I know? This is going to be a negative 12, right? Because it's going to be a 0. So I know two things. So 3 times negative 3 And then what do I get? -2. And what do I do now, right? So I get -2 times -3, which I get 6. So what do I want to know here? So I want to know this has got to be a 4, right? It's got to be a 4. I know it's got to be -12. So what does m need to be? M needs to be -2. Good. Number 14. I think that key made it way too complicated. I don't do them like that. I mean, you should be able to figure out that on your own. Okay, number 14. Find all the roots of this cubic function. So I'm thinking it's a fourth termer. I don't see anything that could group that because this would have to be left with a 2, and half of 58 is what, 27. And no way I'm going to factor out of, I would have to factor out a 21 for the whole thing to go away. So not groupable, but I do know 2 is a root. Cool. So I'm going to break this down to a quadratic right away because it told me 2 is a root. Oops, didn't I say 28? Yeah, I said 27. My bad. 58. All right, so here's my quadratic: x squared plus 4x plus 28. And you're like, really? Would have been nice if that was factorable, and it's not factorable. So I'm going to have to use the good old quadratic formula to solve this one. So opposite b, plus or minus square root. 2 times a is 2, and then I get b squared is 4 times my a times my c. 16 minus, I have to break up my calculator. You get what? 4 times 28 is 112. And then 16 minus 112 is -96. And then what I want to do is find factors of -96 that are perfect squares. What is 96? Another way to do this is just break it down by like the good old factor tree, right? So this would be 32 and 2 and 16. I got a 4 and a 4. It's going to make a pair. And there we go. 4 squared roots of 6. And so it's equal to -4 minus 4 square root of 6 divided by 2. Oh, you know what I did wrong here? This was a 29. What in the world was I thinking? All right. Back it up, 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 back it up. So that was a 29. My bad. I made a quick mistake. Correcting stuff. So back to the quadratic formula with the correct number. So opposite b, plus or minus the square root, 2 times a. Now b squared minus 4 times a times c. All right, let's do this again. So 16. Now I have 29 times, 29 times 4 minus 16. Well, that's a little bit better. I like that. And so I have x is equal to -4 plus or minus the square root of 10i divided by 2. So x is equal to -2 plus or minus 5. Much better. Okay, so there's my solutions. I had the real of 2, and I had 2 complex imaginary. All right, so number 15. It says divide by x plus 3. It didn't say long, so it's linear, so I'm going to put -3 and I'm going to do it synthetic. And I get 6. Let's make sure I'm staying on top of my game over here. Okay, got everything written. Okay, -18. And then -20. And we get positive 60, so I'll get a remainder of 63. Seems quite large, so I'm just going to double check my work. So I have -2, +3, -2, and a 3, and I'm going to synthetically divide, bring down my -2, I get 6, add my 3, get 9, 9 times 3 is, whoop, whoop, 9 times -9 is -27. I think this helps my case though, -29, and 29 times 3, 6, 8, this is a meter of 90. Well, it went from bad to worse on the large, but then I also feel like ended at 90 that was pretty good. So there we go. And so it wants me to write it in a specific way, right? So x plus 3, and what am I left with? This is a cubic, so it's a quadratic plus 90. There we go. And number 16, almost done. It says if I have p of x is equal to x cubed plus 2x squared plus x2, it says has a factor, so let's synthetically divide it. 1, 2, 1, 2, and 1, -2, 0, 1, 2. This is x squared plus 1 and 2. So that's one way to write it. And then I guess my second one is to write all the factors out. So this would be x plus 2, and then this one would have given me the over c means over complex, so minus I plus I, right? So 0 to solve it. I would have gotten my complex solutions. Okay, number 17. Okay, so I, -I, 2, and 3. But this is a nice one for roots. So they gave me both complex. I didn't have a hidden one. So I'm going to multiply this real out. I always like doing my real numbers. And then these are already complex conjugates, so x squared, and then this is going to be a plus 1. Now I'm going to multiply these two together, and I get x cubed, x to the 4th, minus 5x cubed plus 6x squared, and I get x squared minus 5x, 6 to the 4th cubed, 7 squared, 6 x. Okay, just double check I got that one all right. X to the 4th minus 5x cubed plus 7x squared. Yep. Okay, number 18. Find all the zeros and factors of this and just sketch and determine Okay, let's do it. X to the 4 plus 3x cubed is 30x squared minus 6x, 56 0. All right, so the first thing that I would do on number 18 would be find all my possible, what I want to synthetically divide by, which my possible rational roots are just going to be end up all the factors of 56, plus or minus 1, plus or minus 2, because 56 divided by 2 is 28, plus or minus 2 over here is 56. And then 56 divided by 3 doesn't work. 56 divided by 4 is 14. And then 56 divided by, and that's just 8 and 7. Okay, so then I want to pick one of those. I'm going to break this fourth degree down. I'm going to pick 4. 1, 4, 7, 28, negative 2, negative 8, negative 14. And I'm going to assume that's negative 56. And then I'm going to pick another real because now I'm down to a third. You could try grouping this one. Grouping would work. So if it was me, I would just put my third degrees on here. And I'd be ready to group x cubed plus 7x squared grouped with negative 2x minus 14. Whenever I have 4 terms, just look. You could have looked there on my factoring and said, hey, I noticed that I pull out the same factor out of both binomials. We left the same part underneath, so it would have been with x squared minus 2 times the common factor x plus 7. I would have gotten x equals negative 7 as my other solution. And then I had x squared minus 2 equals 0, x squared equals 2. This time I get 2 more real, they're irrational. So what are all, these are all real. So 4, x equals negative 7, and square root of 2 and negative square root of 2. Now, if you didn't do that, you would have had to find 7 and synthetically divided with 7 and broken this down one more time. Yep. Oh, it's negative 7. I was wondering what was going on. And you'd have had to broken this down one more time. And then you would have gotten x squared minus 0 and found it that way. Okay. Number 9. Wait. Not done. So how many real roots? These are my real. How many total roots? Well, there were 4. What's the domain? Well, let's take a look. Well, the domain, of course, is negative infinity, infinity. What is the range? I'd have to put that in my calculator. I'm just not going to do that. So you can look that up in your calculator and find the min and maxes. What is the end behavior? Well, this is an even positive, so it goes to negative infinity, up and up. That acts like a quadratic, and a quadratic that has a positive x squared goes up and up. How does p of x plus 6 more differ? Well, then it gets shifted up 6. Remember, that's just function notation on a shift. It doesn't matter what polynomial you'll have. Add the 6, it's going to be shifted up 6. How many real roots does p of? Well, it's going to be the same degree, so it would You would think it would still have the possibility of having 6, but you'd have to graph it to see that the x-intercept only hits twice. So that's all I'm going to say on that one. So number 19. Put into vertex form by completing a square. Lovely. Back to the beginning. Right. We did one very similar to this. So let's kick off the thing that doesn't make it a perfect square. That's that -8 with a nice positive x squared with a 1. So I'm going to take half of 2, which is 1 squared is 1, and say, oh, that's actually x minus 1 times x minus 1. And since I added 1 on this side and I'm on the same side of the equation, I got to subtract it off so I have 0 impact on my equation and don't create a new one. And so my vertex here is -9. And easiest is to factor this thing if I could, right? You could solve that, but factoring is so much easier. So x minus 4 times when it's like this is 2. So x-intercepts at 4, -2. Okay. And numero 20. And this is just one of those ones. It's like, oh, this one doesn't have a nice positive 1x squared. So it's one of these in the difficult cases. But I'm still going to say get away 5, right? And I'm going to zoom in this picture. I'm going to say I want to make this a perfect square trinomial. You can't make a perfect square trinomial with a 2 in front of the x squared. This is not going to happen. And remember, when you write it in vertex form, you want this x squared, this x minus 1 squared, or whatever it is. You don't want a coefficient with the x. You never see that. So I'm going to have to factor out that stretch at 2. And then I can already tell I'm going to hate this problem because I have to divide 3 by 2 and then square. So half of 3 is 3.5. Squared is 9/4. And that's still going to factor to a nice perfect square trinomial. Don't use decimals, okay? Or beyond that, algebraically, decimals, yucky. Don't do them. Okay, so I know my x value of my vertex is -3/2. I could prove that by doing opposite b over 2 times a. I can tell you that that's what I should get, right? So I know I'm good there. And now what I want to do is I want to get rid of what I had to put there to complete the square, which is not, I didn't add 9/4. Remember, I have this distributive property of 2. So I have to subtract off 2 times my 9/4, which I have to subtract off -18 divided by 4, which is -9/2. And I can write 5 as -10 divided by 2. And I can get x plus 3 squared 2. Okay, and then my vertex is -3/2, comma, -19. And that's the end. Thanks. Hope that helped.